Hey everyone, welcome to MLC's Research Jam 29. Can't believe it's been 29 of these, but it has. We have a few speakers today that are going to be recorded that we can share later. First up is Justin Jung presenting a pretty cool interactive demo of a 3D model. Justin, you want to take it away?
Yeah, thanks for the sort of introduction. And yeah, actually, big shout out to Jason. I guess the MLC community has been a very kind of motivating factor in kind of getting this to work. But yeah, I think today I wanted to show something hopefully sort of fun. I know that, games kind of, is, very entertaining. And I think, maybe depending on your era, but a lot of us might be familiar with Minecraft. Um, and so what I want to present is my work on using discrete diffusion to generate these sparse 3D structures, particular voxel structures. Um, and in particular, what I would like to demo is this interactive sort of uh, demo where you can essentially generate and see the sort of discrete diffusion generation process. So here's just an example of like a video of a, kind of like a previous generation. But actually in this website, what is possible is to generate an actual, can you see my screen, by the way? I realized that I
Yeah.
did not download. Okay, cool. You can actually see the generation process and sort of like interact with the sort of environment. So one thing I have to note is that unfortunately the sort of viewer does not render some complicated blocks. So like chests, for example, and things like that are question marks. And stairs and beds remain question marks. Um, but I guess like generally you can see how it generates this kind of structure. And importantly, we always want to see how this compares to other baselines. So why use discrete diffusion? Autoregressive sort of generation is very common for many things. So why not consider autoregressive methods? And so we can compare both. In particular, what we'll see is that if we turn off the filtered method, this is going to lead to structures that are that may have more complicated blocks. So basically, the filter is removing structures that have a lot of these question marks because this renderer just can't support it. But if we actually look at what the actual sort of like generation is looking like, so there's this really cool sort of interactive demo. Can you see? I'm hoping you can still
Yeah,
see
we can
the
still
other
see.
tab.
We can still see.
There's a much better sort of renderer that I tried. I reached out to them, but they didn't. It's not open source, so I couldn't figure out how to integrate it into the site. But basically, if we take a look at the blocks, like you'll see, like it'll have like a fence, for example. So this might be the question mark blocks, and things of this nature. And so it seems to generate decently realistic. You'll see like slight errors, right? Like there's like a mismatch of some kind of block patterns. But generally, it's pretty exciting that it's able to generate something that looks decently sort of human, sort of inspired in some sense. And this is trained on only 1,200 samples total. And importantly, this generative model is it's not just like mapping, a structure to some particular layout for the same kind of like occupancy map. It actually generates multiple different styles. So here's like different sort of kind of configurations, I guess, like of the same sort of occupancy structure. It generates different like looking structures. Um, so yeah, I guess like just wanted to give a sort of like an interactive demonstration that discrete diffusion can generate these realistic structures. Um, Currently, it is conditioning on an occupancy map. I think some interesting future work would be to learn a generative model that can generate this occupancy map, to have like a fully generative two-stage process. And this work has been accepted as a workshop paper. But yeah, thank you for listening, and you can feel free to give it a try as well. But happy to answer any questions, or yeah, I'll let Jason take the mic.
Can you put a link in the chat?
Definitely, definitely. Yeah, so this is live. So basically, I think you guys can actually interact with it. Um,
Awesome. Question, so what data set did you use? You mentioned, I think, 1,200 examples. But where is this from?
Yeah, so there's a 2019 paper from FAIR where they tried doing like this auto-regressive generation, but that was quite old work. So I think like they weren't able to really do generation. It was more like in painting or like partial generation. It's like called voxel CNN. They released a data set. I think it's like 2,000 or so structures. But then I filter for structures that aren't extremely large and things like that. Right now, my transformer kind of sequence length is like 1024. And then there's like some other things that I filter for, and then it ends up being like 1,200 training samples.
Hmm. And then you mentioned, let's talk about the autoregressive model first. This is autoregressive. It's generating one cube at a time, I guess, conditioned on one voxel at a time, conditioned on all previously generated voxels. Is that right?
Yeah, and then it's like a start, it's like a sort of arbitrary start token in the beginning. Yeah.
And you're doing this, you mentioned conditioned on a specific, like what sort of skeleton, like fill in these blocks, but don't fill in these blocks.
Yeah, so one thing I will say is I initially tried starting this by doing everything fully generative because I thought that would be cool. But the big problem is that it is sparse. Like it's actually like 99% air. Like I don't think you sorry, I don't know why this mouse is not working. I don't think we can see it too well, but like the air, if you look at the air blocks when it's not being rendered, it occupies most of the volume. So even with like inverse class weighting, which I show in the paper, it fails to really generate anything kind of like coherent. And so I had to condition on the actual sort of occupancy. And so that's going to be like positional encoding in some sense, right? So each block, um, like the ones that are supposed to be filled in non-air, you kind of give it a coding of where it should be.
Gotcha. How do you pull those air versus non-air skeletons directly from the data set?
Yeah, so currently the Boolean occupancy maps air versus not air is from the data set. And then I guess the important thing, again, to make sure this is a generative model and it's not just like learning some kind of mapping function, is that it generates multiple very diverse structures for the same, even for the same air not air Boolean occupancy map.
Hmm.
Yeah.
Looks pretty cool,
Cool.
Justin. Quick question. So the diffusion, discrete diffusion, it's just like filling in squares at a time, like roughly at random. That's the algorithm.
Yeah, I mean, I guess the particular discrete diffusion algorithm is the masked discrete diffusion, and so and you're right. It basically starts with all masks, and I think when you see, I kind of model the mask as these question marks. Um, but basically, the yeah, and there's a certain reverse rate parameterization for how much like the probability of like unmasking at each time step. But yes, that's the basic idea, is that like you start with fully masked. Okay, this mouse not working is weird, but yeah, you sort of like unmask, and then by the end you have a completely unmasked or your generated structure.
Cool.
So if it's diffusion, then it's not autoaggressive, right? But you were saying something is autoaggressive.
Oh yeah, so the method which I present is diffusion, right? But yeah, I also consider a baseline where I use the same backbone, but I then use an autoregressive sort of formulation just to see why discrete diffusion to motivate it. And the thing is that autoregressive, and obviously it's kind of, oh, this mouse really not working. The autoregressive turns out that it's not, because it doesn't sort of, you can't generate like anywhere in the space. You have to like condition in a sort of raster scan order. It ends up kind of collapsing. Like for example, like it'll have like huge amount of like one block type for like a lot of the structure, for example. So the discrete formulation is very kind of flexible, right? You can generate sort of any token in the sequence, right? And so it lends itself to more sort of like spatially coherent structures.
That's great. Great that you have this baseline. So all the model takes as input is just an occupancy map. Do you have any?
Yeah, so for now, unfortunately, it does condition on the occupancy map. And then that's the positional encoding. And then it generates based on that.
Then how does it know to generate like houses? Seems like all of them are houses.
That's what it's trained on, right?
Yeah. For now, it's trained on houses. I
Houses,
think I
okay.
have some people who are like, no, you scale this up and make it text conditioned, and you can generate different structures. But some engineering work there, I guess that's TBD. But yeah, it's trained on distribution of houses.
I see. I think it'll be useful to show a few samples from the training data so people know like, oh, they're like houses, but they're different from the generated ones.
Definitely. Um,
That's very cool.
You mentioned this got into a workshop. Which workshop?
It's the like nerve structure probabilistic inference and generative models, like SPIGM. Yeah.
Awesome. You're gonna go in person and present?
I think so. Yeah, I think I will be there.
That's
Yeah.
great. Congrats.
Congrats.
Great.
Thank you. Yeah. And thanks for Jason for encouraging me to submit a workshop paper. Yeah.
Justin sent me an email and the email had a lot of good content, and all I said back was, "You should submit a paper. This is great." And it worked.
It's always a good suggestion.
Yeah. I don't know if I would have without his without your sort of like prompting. But yeah.
Awesome. Well, thanks for presenting. We should probably move on to the next speaker. I think Anuj is not here. So Atharva, do you want to share screen and present next? We have Atharva Bhutani presenting
Yeah,
accuracy
sure.
trade-off in n-bit neural networks.
So is my screen visible?
Yep.
Right. Okay, so let me just put this into full screen. All right. So, hello everyone. Good evening, good morning, based on whatever time zone you're in. I'm Atharva Bhutani. A quick introduction. I'm a 16-year-old high schooler. I'm currently figuring out ways to make neural networks more efficient and faster. Right, so today I'm going to be talking about binary neural networks. Right, so binary neural networks are essentially neural networks whose weights and activations are just purely zeros and ones. And just a quick disclaimer before I move on to any further explanation is when I talk about binary neural networks, I'm referring to sub-byte n-bit neural networks like 1-bit, 2-bit, or 3-bit neural networks as a whole, right? Not just 1-bit networks. All right, so first I would like to disclose the like novelty of this research. Binary neural networks themselves are not novel. They have been researched before. Papers like DoreFaNet or Microsoft's famous 1.58 bitnet paper have already discussed about binary networks in depth and the advantages that they have. Their advantages being they reduce the computation required, they reduce memory footprint, and they increase speed exponentially. But what I felt like was that those papers were just focused on academia because the proposals that these papers made was that binary neural networks are really huge and they can give various improvements in the current machine learning and deep learning sectors. However, they are not being used anywhere currently in practice. So it feels like the papers were just built for educational purposes. But we can actually use binary neural networks in real life, and a lot of people will say that they are being used in edge AI or drones or IoT devices. But what is actually being used is quantized models, and quantized models are not really binary neural networks, which is what I will explain in the future slides. So first I would like to focus on quantization. Right, I would like to talk a little bit about quantization and how I feel like quantization is not a real way to achieve binary neural networks. So I'm sure everyone here knows what quantization really is. It is just taking a big model and then reducing precision and cutting it down and down into whatever bit width you like. But I believe that the main reason why binary neural networks and quantized neural networks have such a bad reputation of not having enough accuracy or not having enough precision or not performing as well as they're supposed to, the root cause for that is quantization. And quantization solves very big problems, right? I'm not saying that it does not solve any problem. It solves the major problem of inference, right? We need, if we want to run inference on a very small device, we cannot run full 32-bit large language models on it. We need to quantize them down to 4-bit or even 1-bit and then run them. But this inference problem is solved. However, two problems are still left unsolved. So the first problem is the problem of a training cost, right? So we do still need a full precision model, a full 32-bit or a 16-bit model to be able to quantize it, right? There is no such way that I know of that we can build small models from scratch. This is what I will be proposing, but I do not know a current way to build small models from scratch. So we need a full precision model and we need to pre-train it, right? So a lot of people will say that you can just grab a model like Quen or DeepSeek and then quantize it down. But for various use cases, you cannot just take an existing pre-trained model and quantize it. You need to pre-train it yourself, and pre-training it yourself means hundreds of GPU hours and a lot of energy, which a lot of people do not have access to. Right. And the second problem that we face is precision loss. As I already talked about earlier, uh, the quantized models lose a lot of precision. It is obvious if you take a large model and you keep cutting it down into a smaller model, it will of course lose accuracy. But the accuracy loss and the amount of energy that we give it, it is not a good trade-off. Not a good trade-off, I believe, and I believe that we can do something better than this, right? And as I said earlier, this is the reason, like this precision loss is the reason why a lot of people say that binary neural networks are not worth it. Right. So here is a quick illustration that I made. These all these values are estimated, by the way. I'm going to be actually the research that I'm doing is going to be figuring out the real values for this. But here is a basic quantization pipeline that you take a baseline model. Let's say it has an estimated accuracy of 98%. Then you keep quantizing it and you keep losing accuracy or up till, let's say, 1 bit. So you lose 10% of accuracy, and 10% of accuracy is not something to just look over, right? And then you have obtained a 1-bit network with 89% accuracy. Whereas if we look at Boolean networks, so if we just train a naive network without any tricks, any gradient estimation tricks or anything like that, it does not even give us 83 and 85 is just pushing it. It gives us barely 75% accuracy. And that is what people compare to. People compare this quantized model to a naive network trained up till 75% accuracy. But there are two reasons why this is not a good comparison. One reason is the 1-bit quantized network was already trained based off of an intelligent 32-bit baseline, right? We already spent a lot of computational power and energy into training this 32-bit baseline. Then we quantized it, so it already knows a lot of things, but it obviously has lost precision. Our naive network, first of all, is trained on a exponentially less amount of energy and compute as compared to the 32-bit baseline. Also, it uses the same amount of data as our old network, but it uses a lesser amount of energy. So a good comparison, I believe, would be to give both a quantized network and a Boolean network the same amount of energy to train on. Let's say this is just an estimate. I know it does not take that much energy, but let's say our quantized network in pre-training and quantization uses 100 units of energy. So our naive network will use barely 5 or 10 units of energy to train, and it will train up on the entire data set. So we can give it more data until we reach that energy threshold, and in reaching that energy threshold, it will use exponentially less computational power than our quantized model takes, right? And that is what I am trying to build Atlas on top of. So Atlas is a framework which proposes to build binary neural networks from scratch themselves. So it is completely opposite to the idea of quantization, right? So we build binary neural networks, byte level neural networks from scratch. And how is this efficient and not just taking one value and then wasting 7 bits? Is that the bits are packed. So let's say you have a 1-bit neural network. So one given value will contain eight representational values, right? So then it is packed according to that, and it supports bitwise operations, so it does not use floating point operations. A binary neural network is a network that uses binary operations for its processing. If you go back to this example, um the naive Boolean network, or any network which is trained as a Boolean network, uses binary operations. So it does not need an external accelerator which accelerates its floating point operations, which GPUs do for our current uses. GPUs accelerate floating point operations, but the computers that we have already excel at binary operations. And if we were to build accelerators, I believe that we could reduce the computational power needed and reduce the energy consumed exponentially even more. Right.
Yeah,
So
Atharva,
now
I have a
let's.
question.
Yes.
Um, so I guess we have a couple possible sets of issues. One is, can you computationally implement something that's quick? And it looks like this library is a solution to that. So implementing efficient, bit packed, inference and maybe training. This is
Yes.
second set of things we should consider, which is kind of mathematically, let's say you have a data set and you can train a 32-bit floating point model on it using gradients and so on.
Right.
Can you, does it actually work to train a similar 1-bit model? Do the gradients work? Does the learning work and the parameters change as we might expect?
Right.
Can you speak a little
So
bit to that? Also, I should say we're getting close to time, but
sure,
I don't
sure.
want to push.
It's just about to end. I'm just about to
Okay,
talk
okay.
about the future prospects of it. Right. So the thing that you talked about, gradients. So we cannot actually use real values like floating point values, because gradients are in floating point values. You cannot just take the gradient of a gradient of a constant, of course, zero. So if we cannot do that efficiently. So what binary networks do is we estimate the gradients. So it is I don't know if if I should call it a framework, but straight through estimators are a method which we use to just give an estimation of the gradient and then train the model with the model is under the illusion that it is being trained with gradients, but we're not actually using any gradients. We're just giving it the illusion of it. So that is able to give us good training, but as I said previously, that accuracy is lost, right? And one thing that we can also implement is the activation functions. All of the activation functions that we have currently are based on real values. So we can replace them with threshold functions. Like if our value exceeds a certain threshold, then we exclude it. And if it is under our acceptable threshold, we can use that value. Right. And now, for the precision loss problem, this is a score that I propose. It is not a score or a benchmark in a mathematical sense, but it's a benchmark in the sense that it helps us categorize models on how efficient they are. So this is an example plot that I did. The research is actually, I'm actually in progress of doing the research. This is just some example values. So we can actually see that a 32-bit model uses 1 unit of energy and gives us 95% accuracy. And if we look at the sweet spot, a sweet spot is decided on how much compute we're reducing. So we reduce compute by 7 points, and we still retain almost 90% of the accuracy. So if we operate within the 4 to 8 bit, like 5-bit, 6-bit, 7-bit model space, I believe that we can not only break even but also overcome the lost accuracy by giving it approximately like 90 to 80% of the computational power that we gave our original 32-bit model. So these are just some example plots of how compute cost falls down when bit precision falls down. Like 1 bit uses a lot less energy as compared to a 32-bit or a 16-bit model, but accuracy also falls down along with it. So the compute accuracy trade-off is actually a benchmark which uses both the compute cost reduction and the accuracy reduction, and is able to plot a graph on how efficient a given model is. Right. So I'm just going to take 5 more minutes and talk about how I believe that Atlas can actually be useful, because I previously said that binary neural networks are not being used anywhere currently. So I
Yeah,
believe.
Atharva, we're pretty much at time. We used up
Sure,
the
sure.
9 minutes plus the 3 minutes. I think this is a really cool idea, and it's awesome that you have this library implemented. I think it'd be really nice to see um, actual training results when you have them. I realize
Sure.
that, it's actually a long research direction to use straight through estimators and these types of training tricks to make models train well.
Right.
But I bet we could all learn a lot from actually trying some training runs and seeing how the models perform.
Sure. Yeah. So I'm actually
These
really
are,
close to implementing a training pipeline. So when
that's
that's
great. That's
implemented,
great.
I'll just shoot somebody a message, and then we can maybe talk about.
Yeah, that's
to
awesome.
see more.
If people want to contact you and chat about this more, get in touch, maybe even help
Right.
the best way.
I have a slide at the end. So I have my Twitter here, and if you want to email me, you can email at any of these two email addresses. So if anybody
Awesome.
wants to contact, I would love to collaborate with somebody because, of course, doing this as a high schooler alone is kind of difficult. So if anybody wants to collaborate and help, all collaborations are open, right? I'm just here implementing ideas that I think will be useful in the future. Right.
Awesome. Thanks so much. Thanks so much. And if you want to come back next time and show any, any progress update or whatever, we'd love to have you.
Sure, sure. I'd love to. Love to. Thanks a lot.
Awesome. Thanks for presenting. Up next, we have Bryce and Raymond presenting miscellaneous updates, I think, including LoRa adapters for math and maybe an update on the loss landscape volume stuff they talked about before.
Sweet. Do you want to go first, Raymond, or should I?
I think you should probably go first.
Okay, sounds good. I'm actually going to present a different subject. Hope that's okay. This is what I was planning on presenting last time. But I think, yeah, this is actually something I would caution you as well. Our last presenter, just that the engineering of getting these systems to work is much larger scope than I think you, in general, like most people are thinking about. And I kind of realized this was also the case with the other idea that I was going to present after kind of talking with Lynn and Raymond. But yeah, let's talk about improving sample efficiency in LLM reinforcement learning. And then Raymond will talk about generalization. But sorry. Okay, so here's the inspiration. So those of you who are familiar with the literature, AlphaGo 0, in comparison to the previous versions of AlphaGo, swapped traditional reinforcement learning to instead actually try to predict the results of Monte Carlo tree search, and was then trained in tandem with Monte Carlo tree search on said results. And kind of the brilliance of this is that we went from a version that took several months to train to, in 36 hours, the new version, the reinforcement version surpassing it. So we get like a pretty insane speed boost by doing this. And yeah, basically the intuition that I'm kind of going for here is that in general, learning from experience is very slow, and sometimes it's completely intractable. So one of the examples, another example is this Montezuma's Revenge, classic Atari game. And basically, the rewards are so sparse in this game that your random exploration of reinforcement learning cannot make any progress. So you need new or different techniques. And so this is an example of where this approach would also be perhaps applicable. So basically, I kind of have this like spectrum here of kind of the different ways we can go about training models, right? So on the left, we have learning from specified data, and this is really most of our learning paradigms. We have supervised learning, unsupervised learning, self-supervised learning. And on the right, we have learning from experience. Now, the like core traditional reinforcement learning algorithms fit in this category. And I believe in most of these labs, we're also doing this with our thinking LLMs. We're just doing reinforcement learning to try to see if we can get some better results. But there's actually kind of a middle ground, right? And that's where I put AlphaGo 0, which is, it's not learning directly from experience. It's learning from, having this Monte Carlo tree search built into the algorithm. And there's also a larger category of model-based reinforcement learning. So, okay, now if we go back to our AlphaGo example, we basically are able to rely on Monte Carlo tree search as a policy improvement operator. Now, this is very specific to tree search games and was the leading paradigm prior to combining it with neural networks. So kind of the question I'm thinking of is, what policy improvement operator can you apply to today's large language models? The answer, at least one proposed answer, is to use LLMs once again. And we're kind of already doing this with synthetic data, right? we are training our models on something that is, actually partially an output from the language model. And so there's actually a wide design space here of what precisely you do. And I don't want to specify an exact recipe, but the rough idea is we take our LLM, we get some outputs, and instead of learning directly from that output, we do some additional processing and learn from that. And it's kind of like lots of ways to take this. One idea I have is in context learning is much more sample efficient than reinforcement learning, right? So imagine if you're trying to solve the problem, but you have an example attempt at the problem already in your context window. How does that change how fast the learning procedure will then continue? And the other thought is that you actually know the answer to these RL problems, and you can potentially use that to kind of steer the trajectory to already, end with a reinforced positive reward path. So I don't have any specific implementation of this. I have implemented it, but I showed you guys earlier my core RL algorithm. It appears to have a bug. I'm not entirely positive. Yeah, anyway. So like advantages here, obviously the big one is to try to do reinforcement learning faster. You might get better performance at convergence, unclear. And then something else that's actually kind of interesting is I think this will give you much more control over the converged policy, depending on how you use it. So something that the field is, in my opinion, struggling with is you have these thinking models where you ask the model, hi, and it thinks for 3 minutes and then tells you hi back. Why is that happening? It's because this is trained on reinforcement learning to produce all these tokens because there's so many times when producing those tokens gives it positive reward, right? But we don't actually need all those tokens for such a simple problem. And this kind of framework might give you a better control over the behavior in that scenario. Because you do see if you get rid of the thinking responses when it's primarily supervised fine tuning, you get a much shorter response when the answer can be concise and a much longer response when more detail is needed. That should be able to be applied across thinking models as well. And I think that the field just hasn't quite figured that out yet. But that's all I have. I don't know if there's any questions or we can hand it off to Raymond.
Thanks. Yeah, cool. Any quick questions? I have one general thought, not so much a question, but it seems like there might be two different worlds here. In one world, we can run a model or rollouts or Monte Carlo tree search toward and at the end we get a reward that is maybe like known to be correct or verifiable in some cases. Or in the Monte Carlo tree search, I guess you run a long search and you get to some maybe board game state that's the policy model says, this is in fact correct. I'm glad you found this after 10 steps down this long tree, but you found it, and now that you know it's correct or the best possible board, then trained to get there more quickly. In other cases, it might be hard to have any kind of reward at the end of this rollout. For example, if you're using in-context learning, like maybe you have an LLM that says something, but it's a little bit hard to say that it's correct. So I wonder whether the limit is actually the rollouts, or is the limit the ground truth data about what is actually worth rewarding versus not, like the labels.
Certainly. I think, yeah, a lot of people are kind of saying the same thing. It's all about like, where can you get the verifiable rewards? And that's why people are focusing primarily on these math problems where we have the answer already.
Right.
I'm focused still on that regime where we actually know the reward. And it still takes, some non-trivial number of RL steps to take your policy from the original, pre-trained model or maybe instruction tuned model, and then get to your converged RL policy. And yeah, the question is like, can you do this faster? Do you have more control over it? In which case, yeah, in this regime, we already know what the rewards are. And it's just about, trying to get there more efficiently.
Makes sense. Other thoughts, questions? If not, maybe we go on with Raymond, and we can circle back if anyone wants to talk about this more.
Sounds good.
Okay. So I'm going to be talking about my research, which is on why is generalization hard, specifically why do we need data? And to motivate the stuff that I'm going to be talking about, we can think about MNIST. If we train MNIST with more data, we know we get models which are better. As you can see over here, if we train with 60,000 examples, then we get pretty close to 100% accuracy. But if we train with only 600 examples, we get pretty terrible accuracy. And what's interesting here is if we look at the training loss landscape with respect to 600 examples, you can see the model that we get, the 600 example model, but you can also see the 6,000 example model, the 60,000 example model. And then if we look at the training loss landscape with 60,000 examples, this is what we train our gradient descent with. We'll see that the 600 example and 6,000 example have basically disappeared as minima, and the 60,000 one is the only one left, which will explain why we get it. But the answer that I want to answer here is why don't we ever get models that are like 60,000 or 6,000 in performance when training at only 600 examples? They sort of look viable here, but I think you can sort of tell reasonable explanation just from this graph, which is that this one seems to be way bigger than the other two. And so purely from a probability perspective, we're just always going to get this one. And we can't really make this precise here because this is like just a slice of a high dimensional landscape, but that's what I'm going to be motivating as my future work. So there's this idea known as the volume hypothesis, which claims to explain generalization. Specifically, it makes a claim that flat minima generalize well, which is a pretty old idea in this literature, and that gradient descent is always going to find the flattest minima because the flattest minima are so much larger than all the other minima. In this view, we see that generalization is almost very, very easy. We're almost guaranteed because gradient descent is always going to find them. And to do this experiment to test whether or not these claims are true, previous literature has looked into how can we measure the sizes of minima. Specifically, a minima size is determined by how much we can perturb its weights without increasing its loss a lot. And to measure this, we use a technique called Bayesian volume estimation. We start from some sort of minima, we choose random vectors in weight space, we perturb along those vectors and see how much the loss increases. Once we hit a threshold, we say that's the edge of our basin, and we can estimate the volume of that basin. Unfortunately, this is a Monte Carlo technique, so we're going to need a lot of perturbations, especially with high dimensions. And this will always underestimate the true volume because it only estimates the star convex volume. As you can see over here, all we could ever do with this technique is estimate the red region. We can't estimate the true blue region, which might be the true base. But they used this technique anyways, and in their existing results, what they did was that they generated a bunch of bad minimas. And what bad minimas means here is that you can imagine we have some sort of good classification problem like the Swiss roll over here, and then we just add in some data to samples that are incorrectly labeled, these X's, and as a result, we'll learn something that learns the training data perfectly, but it has a pretty terrible test accuracy. It's basically something that we would hope we would never get from deep learning, and we don't ever get. And what they did is they generated a bunch of these bad minima, these poison minimas, and they looked at the volumes of these minimas compared to the minima that you get without any of these mislabeled samples. And what you found is that the minima you naturally get has a significantly higher volume than all the other minima. And that means that poison minima have much smaller volumes, and maybe the volume hypothesis can explain why we don't get terrible solutions like these in practice. Now, this has some limitations, namely that they only looked at poison minima and explains why maybe bad minima don't happen. But deep learning, we know, needs lots of data. Why? And so what I decided to look at was what are the volumes of good minima and how does data change these minima volumes? And so what I found in my results is that gradient descent tends to find large minima, but there are sharp minima which are better. So here I didn't run experiments on MNIST. You can see here is the volumes across different landscapes. So over here, when I look at the volumes of minima in a 60 data landscape, the minima that I naturally obtained in that landscape with 60 examples by training is larger than the volumes of all the other models. But if I increase the data set a little bit more, the volume of this minima that I found just shrinks to 0. And instead, what I find is at 600 examples, the largest minima is the one that I actually obtained at 600, and all the other ones are way less. So basically, the found minima is always large, seems to be largest in this lost landscape. Minima from larger data sets, which we know generalize better, are smaller. Data will shrink all minimas, and the largest minimas tend to disappear every time. And I also did this for some more problems, and I found, interestingly, there's some sort of scaling law here between MNIST, CIFAR. We see that you can imagine that all these dots, they sort of lie in a straight line, and they do quite lie in a straight line, but there's a scaling law here between the amount of data and the log volume that you get. But it's sort of dependent on the specific architecture using CNN, MLP, as well as the number of parameters. So I don't think it's that interesting, but it is surprising. I will note that in some other
Can I, can
problems.
I ask a question? I don't really understand these plots. Maybe
Okay.
can we go back to the
Yes.
this one's fine. So let's pick a specific line here. Let's look at the green one.
Mhm.
Um,
This is a minima that was trained with 2,000 examples. So I got this by training with gradient descent on 2,000 training examples. And I looked at how big is this minima in, let's say, only 60 examples, lost landscape.
so when you say, so you trained a model on 2000 examples, so the final theta, the parameter vector theta final has been learned through 2000 examples.
Yes.
If you look at the green line, but over to the left, where you're evaluating
Mhm.
it on only, I don't know how many that would be,
60
60
or
examples.
600.
Um, what is that evaluation?
That's the volume in that landscape. Because as we change the amount of data, the amount of the landscape itself changes.
So you're taking the solution found under 2000 examples
Yes.
and then creating a landscape out of a different selection of only 60 examples and looking at that theta's volume in the other landscape.
Yes, but I should specify actually that for my original 2,000 examples, it was trained on these 60 examples plus 1,940 other examples.
Okay,
So
so
it will be a minima in this landscape.
you train on 2000 examples and then you create a new loss landscape consisting of only 60 samples from the 2000.
Yes.
They were asking what is the volume in that different, I guess it would be a simpler landscape because there's less
Yes.
data and the volume is slightly higher, is what you're saying?
Yes. Yes.
Okay.
But it's not as high as the volume of the thing that I naturally get when training on 60.
Okay, that's interesting. Or maybe that's interesting. What does this, yeah, what does this imply? Or
This,
what?
well, this is basically just saying that we find that sharp minima can generalize well, but we're basically never going to find them purely based off volume. And it seems like volume is what drives what we're learning.
All right, maybe I'm a little slow, but can you walk us through that train of logic?
So we know that the one that we find always happens to have the largest volume. That's the case because you can see that these dots always lie above all the other candidate minima. Other candidate minima were trained at higher data settings and taken to a lower data setting. And then I found that their volumes are just so much lower, and that explains why I'll never get them.
Okay.
That's what we see in this graph. And we know that the higher data settings just generalize better. More data is how deep learning works.
So by sharp, you mean smaller volume?
Yes, yes. We're using volume as a measure of flatness.
Okay.
So you're saying that if you want to compare two different solutions, you could have a solution that was trained with more data and it generates an actually slightly sharper minima, but it's actually better. So volume
Yes.
alone is not the best predictor.
Yes.
Okay.
So is the volume the sum of all the minima or just
No, it's just one minima. I found one minima and I used Bayesian volume estimation to figure out what its volume was.
which one? Oh, the same, not the same one, right?
I mean, I take a model here, I have this, and I just try and see whether or not it has a good loss in the training loss landscape of a different data set or a smaller data set.
Mm.
And what I'm finding is that their individual volumes, individually, the one that I found tends to be the largest. Although, actually, I didn't get around to this yet, but I have some other slides, which is there is some cases where it seems like the minima that I found is not necessarily the largest. So over here for a Swiss roll and modular arithmetic, what I found is that if I in ultra low data settings, the minimum I find happens to be largest, but at higher data settings, sometimes the minimum I find is not as large as other minima that I've taken to this data set setting. And I think that's because there's just a large number of possible 50 example minima. I've done all these experiments for multiple seeds, so these results are fairly robust. And the idea here, I think, is that some minima are just more common than others. You can think of it like this. Like the minima that I found in training is represented by this green circle, and then I found like, oh, there's this minima that's larger that I'm not finding in training ever. And that might be because this green circle, although it's not a very large minima by itself, it belongs to a very popular class of minima. And so whenever I train, I always get one of these popular classes because they occupy the most volume overall. Although there's this small minima which has a larger volume than it. But yeah, so I found that this
It could be fun to try to find a different property rather than this random vector minima estimate or volume estimation, a different property that correlates better with generalization.
Well, I am pretty bullish on the idea of model compression, but I haven't done any experiments with that yet. But basically, as a take-home message for my work, I found that much more mild picture of generalization than the original volume hypothesis. Namely that flat minima generalize well. We often find flat minima, but there are sharp minima that generalize well, and they're very unlikely to find them because of small volumes. Deep learning needs data because adding data changes what the largest minima are going to be, so we start to find them. This is sort of like a cartoon over here, where we imagine that we have a bunch of minima, some are sharp, some are flat, and deep learning is always going to like this flat minima until we just increase the amount of data and that flat minima is no longer possible. And this sort of makes sense because we know that a lot of sharp minima from our poisoning experiments are pretty terrible. But in this sea of sharp minima, there are some gold mines there that we're just not ever going to find because deep learning just doesn't want to find them based off volume. That's my takeaway. These are my results. I'll take questions.
So this does not characterize how many minimas you can find
Yes.
as you increase data, right? So it might be
Yeah.
that as you increase data, minimas are sharper, but there are more of them.
Yes. But the thing is, we also know for as we increase data, the previous flattest minima just shrink and vanish. And so that's another explanation for why we're finding sharper minima, which is that these sharpest minima are now the biggest minima because the previous biggest minima got erased.
I think so. There's a general trend that the volumes decrease as data is added, and I think it kind of makes sense because there's less flexibility in your parameters in the loss landscape. But
Mhm.
it's still the case that gradient descent is finding the larger minima, not always the largest, but some of the larger ones. And then as soon as your loss landscape becomes more representative of the true distribution, then the minima that you find is indeed something that stays low on the loss landscape of the test set.
Could be worth comparing these measures to a couple others. One could be kind of the intrinsic dimension, like I think we talked about in the past.
Mhm.
How many
Yes.
parameters are needed to model the data set? A second could be in these same experiments, when you find the minima, rather than taking random vectors and kind of finding how an estimate of the volume, just take steps from your solution as steeply as possible to kind of raise the loss above some threshold. So kind of like find the nearest possible wall in the space. So it's sort of like if you assume the volume is a sphere, how big can that sphere be before part of the sphere is ruined?
Mhm. Well, one thing I haven't included in here, but I looked at the histograms of how far I could go on each direction, and all those issues that I worried about in my last talk, it turned out I don't really have to worry about them. The difference in the volumes of the minimum I'm looking at are so dramatic that no matter which of these ideas you're taking, it's clearly obvious which one is biggest and which one is smallest. There's no mistaking these minima, at least in this case for MNIST. This one at this landscape is clearly much larger than this one by any metric you use.
Well, maybe. So these metrics are based on random perturbations.
Yes.
In high dimensions, things might behave differently. So if we have 100,000 dimensions, almost every direction you find you'll be able to go pretty far before you hit before your loss
Mhm.
increases. But there's actually a wall right here that you just can barely find because all these random directions, because there's so
At
many
the
ways
very least, I
to do it.
never found any of them, so I would have to do from the 500 I did over 500 perturbations, and from those I found that there was basically no chance that I would ever mistake the big minima for the small minima. That's just how different their volumes are. I know there's an error associated with Monte Carlo, but it seems experimentally the difference in volumes is just so large, I don't have to worry about it. It's like you don't need a microscope to tell an ant is smaller than an elephant.
Yeah, I guess I'm saying we could try a different definition of large versus small rather than this volume estimation. We could use what is the distance to the nearest high loss point, which if it's a small point could be
The thing is, it's going to give the exact same results. I can tell from the histograms of
maybe
how
yeah,
it's
it'd be
gone.
nice to show.
So how do you find the nearest wall without randomizing a bunch of directions? You
I
still
would just take the direction of steepest ascent. So do gradient ascent from where you are, take a couple steps, and then also try to minimize the norm. There's some papers that have done this. Basically, you take steps, you pull it back towards zero, and then you take a step uphill, back towards zero, uphill. This will find a solution that's like kind of like the minimum distance away, but has high loss.
Yeah. Yeah, that's a good point. Even if you can just run that and see that if that distance was ever representative in your random distances. When you calculate your volume, you have a bunch of distances, right? And if you use the gradient ascent, find that distance will be smaller than the others probably, but how much smaller?
This is sort of like SAM, right? Sharpness aware minimization. You go in the ground, you find the largest point.
Yeah, I think they might have done that, the same optimization.
Yeah, but that will be using it in the training process, using it as a
I've actually also done experiments with SAM that I didn't show here because of time.
Cool. All right, we are getting short on time. I think David is not here, so we're going to wrap up the recorded portion. For people watching the videos later, thanks for stopping by. If you'd like to present some future research jam, we have these every, depends, 6 weeks or so, maybe 8 weeks. All right, thanks for joining.